Hello friends, welcome back. In this video, we'll dive into Chapter 2 of NMR Spectroscopy. Let's explore first the concept of integration in NMR spectroscopy. Here, we see the NMR spectrum of phenylacetone. Each different type of proton appears at a different place, allowing us to determine the number of different types of hydrogen in the molecule. Integration helps us determine the area under a peak, which is proportional to the number of hydrogens generating that peak. In the NMR spectrum of benzyl acetate, the integral line rises proportionally to the number of hydrogens in each peak, giving us a ratio of 55:22:33, which simplifies to 5:2:3. Using Fort NMR, modern instruments can report the integral as a number, providing accurate measurements of hydrogen ratios. Next, we explore the concept of diamagnetic anisotropy and how valence electrons shield the nucleus. Valence electrons create a magnetic field that opposes the applied field, shielding the nucleus from its full effect. Different types of protons in a molecule have different amounts of shielding, causing them to appear at different places in the spectrum. Highly shielded protons appears upfield and less shielded protons appears as downfield. Friends, let's now discuss about the term chemical shift. Chemical shift expresses the difference in resonance frequency of a given proton compared to the methyl proton of TMS. Rather than measuring the exact resonance position of a peak, we measure how far downfield it is shifted from TMS, tetramethylsilane. Please note that TMS has 12 equivalent hydrogen atoms, all in the same chemical environment, producing a single sharp peak in the NMR spectrum. This makes it easy to identify and use as a reference. Stronger magnetic fields cause the instrument to operate at higher frequencies, affecting the NMR spectrum. Higher frequencies result in larger shifts in Hertz for a given proton, influencing the observed chemical shift. We can adjust the shift to a field-independent value called the chemical shift, measured in parts per million, ppm. 1 part per million, ppm, represents a specific change in magnetic field strength or frequency, providing a standardized measurement. NMR correlation charts help define ranges for different types of protons, aiding in spectrum interpretation. Friends, don't worry too much about the exact values and positions. It's usually enough to understand which types of hydrogens appear in the different regions of the NMR spectrum. 3 major factors account for the resonance positions of most protons: deshielding by electronegative elements, anisotropic fields, and hydrogen bonding. Friends, let's now concentrate our focus on the concept, deshielding by electronegative elements. Electronegative elements like chlorine deshield the proton, moving its resonance to a lower field and causing it to appear at a different place in the spectrum. Electronegativity significantly influences the chemical shift of CH3X compounds. As the electronegativity of atom X increases, the chemical shift also increases, indicating greater deshielding. It can be observed from the chart that CH3F is more deshielded than CH3I. Substitution effects on chemical shift show that the presence of more electronegative atoms increases the chemical shift. Additionally, the effect decreases with increasing distance from the electronegative atom. Anisotropic fields, due to the presence of pi bonds, greatly affect the chemical shift. Benzene rings, in particular, have the most significant impact. In benzene, circulating pi electrons create a ring current, generating a secondary magnetic field that deshields aromatic protons, adding to the overall field. In alkenes, the anisotropic field causes protons to be deshielded, shifting them downfield in the NMR spectrum due to the secondary magnetic field. For alkenes, the anisotropic field results in shielding of the hydrogens, as the fields subtract, leading to an upfield shift in the NMR spectrum. Shielding cones illustrate the areas of shielding and deshielding in common pi systems, with typical chemical shift values for hydrogen atoms provided. Friends, let's take a look on effect on hydrogen bonding on chemical shift. Hydrogen bonding plays a crucial role in chemical shifts, particularly in the deshielding of protons. Hydrogen bonding deshields protons by lengthening the OH bond and reducing the valence electron density around the proton, shifting it downfield in the NMR spectrum. Carboxylic acids exhibit strong hydrogen bonding, forming dimers and causing significant downfield shifts in the NMR spectrum. Methyl salicylate also shows extreme downfield shifts due to internal hydrogen bonding. Friends, this brings us to the end of Chapter 2 of NMR Spectroscopy. In Chapter 3, we'll dive into more details. Take care, goodbye.